All right, so the first thing I want to talk about today is containers. The idea of a container is just a way of holding stuff, right? We know a few data structures that hold stuff, like arrays hold stuff, vectors hold stuff. There's more to it, and so we have slides about it, okay? So there's a bunch of different cool things to do in C++. It's baked into the library. You've got vectors already. Then there's going to be lists. There's going to be maps and other cool things that maybe you've read about in the book. That I haven't talked about in class. So I'm excited. We're just going to discover a bunch of different ways to store things, and we're going to get different abilities depending on how we store the things. All right? So all a container is just a way to store stuff. Okay? So before we get to there, though, I want to talk about abstract data types. All right? Abstract data types, usually we say ADTs for short, because they're going hand in hand with these container ideas. Okay? So an ADT is, if you look it up in like a textbook, it's this. It's a class of objects whose logical behavior is defined by a set of values and a set of operations. What I want you to read when you see that is an ADT is defined based on how you use it, not based on how it's implemented. All right? So just like pretend that this abstract data type thing is just a black box that you can ask it to do things. So like a vector is an ADT. Vector is a black box because you have no clue what's going on inside of a vector, do you? You just know how to talk to a vector, right? You say dot pushback. After you declare an empty vector, you say dot pushback to or something. And then the vector responds like that's a void method, right? So it's like, sure, I did that for you. You have no clue what happens, right, when you say pushback. But as long as the black box plays the game of being a vector correctly, like go to dot at 0, it should be giving me 2 back now. As long as it does that, as long as it responds correctly to all the vector operations, that black box is a vector. We have no clue what's going on inside of it, though. It secretly is an array deep down, but you didn't need to know that. It could just be like storing the data as some weird string and like converting it back to an int when it's done. As long as it plays this game of pushback, dot at, dot size properly, it is a vector. That's what a vector is. It's defined in terms of its operations. It's going to respond to what we ask it to do. We have no clue how it's implemented, and we also don't care as the users of it. Like vectors, they're black boxes. They respond to pushback, popback, at, size, all those fun things. That's what it means to be an abstract data type. We have no clue how it's implemented. It can be implemented in any number of ways. As long as the operations work out in the way that they should, it is a vector for all intents and purposes. Okay? A container is a special kind of ADT. It's just a type that's holding on to elements in a certain way. And those elements can be of any type. Just like, you can make a vector of doubles, a vector of chars, vector of strings. Doesn't matter. So a vector is a container. You can even put a vector of vectors, right? You can have those. A vector of events, like 2 dimensions, 3 dimensions if you want to. And there's a bunch of different container classes that are implemented in C++ along with vectors. In this documentation page, like if you ever looked at it on the side here, if you ever went to vectors, like containers, it's in containers, right? And you have all these other things. Okay? So we're going to talk about the other things too. There's a bunch of different trade-offs because they all work a little bit differently. They hold onto their things a little bit differently. All right. So I guess let's start with vectors because we know those, and we'll explain the things that they all have in common with each other. Okay. So what are vectors? They are a random access container that can grow. Well, we can click on vector and it will tell us that. Right. Click vector, sequence container, contiguous locations, dynamically allocated. Like, read this if you want one day. It's very useful, but all that we know is if you make a vector, you can do .at on it. You can go immediately to a certain place. That's what random access means. You can go to index 5 immediately if you wanted to. Okay, so here's an example vector for the slide. 5. Let's say this is my vector. If this is your existing vector, it has these indices, and you can go to any one of them you want. You can go straight to index 2. You don't have to like start at the beginning or anything. Like you remember linked lists, right? You kind of have to go through the start to get to the middle of the linked list. A vector is random access. You can go anywhere you want, and everything has an index. You can add to the end of a vector with the dot pushback. That's an operation on vectors, right? You can make a new index, like pushback 0. Those are all the operations that you have on the vector container, among other things, okay? And everything has an index in a vector. If you click on any of these operations, like .at, how fast is it? Because we're going to talk about the trade-offs today. You scroll down to complexity. That means how fast it is, how fast it takes to run. This is constant complexity. It's pretty much as fast as it could possibly be to go somewhere in a vector. constant complexity to get to index 2, index 42. Okay, so that's pretty nice. And everything that you could want to do, including pushback, surprisingly, dot add is constant, dot size is constant, even dot pushback, which grows the vector, somehow the complexity of that is constant, with some extra stuff in parentheses that you'll have to wait until a four-year college's algorithms class to fully understand. But that's pretty nice. Pretty nice. Let's see here. So yeah, you're allowed to use all these things. You can get around a vector with the like dot at, to do a for loop, start at index 0, do dot size. There's other ways though. There's these that I've kind of just glanced on, right? Glanced over, but we've used them a little bit. These things called iterators, begin and end, like those also get you through the vector, but I haven't really talked about them in class. You've read about them in your book though, so I'm gonna actually talk about those now. So let's see here. What do I want to do? What is an iterator? If you ask for dot begin, what does that really mean? If you ask for dot end, what does that really mean? Now I get to tell you, okay? I told you just enough to get them sorted, but now there's more to it. So what an iterator does is just kind of like keep track of a place in the vector, and it can move. It can move from start to finish. Okay? So an iterator is like an abstraction over the idea of iteration, if that makes sense. Again, it's abstract. It's like a black box. We want to think of them like pointers, though. Like they have the star operator overloaded and all that works out. But if you ask for v dot begin, it gives you back an iterator. If this is your vector v, it's going to give you back an iterator to the beginning, the very first element of that vector. 8, 6, 7, 5, let's say, if that is my vector. You say, I don't know, if you say it, iterator it equals v dot begin, then it's going to set this it iterator. It's kind of like a pointer to right here. I want you to think of it like a pointer, because if you dereference it, it will give you the value back. Okay, so yeah, v dot begin is an iterator to the beginning of the vector, and the type is really, really weird. It's not just iterator. It's, let's see, vector. If it's a vector of ints that you're iterating through, and you use that vector dot begin, it's going to be vector of int : iterator. It's a type within a type. It's very weird. So that's the type of the thing. It's like a vector of int : iterator. That's it's type. And let's see. You can also ask for the end. Dot end is also an iterator. It's a iterator not to the last element, not a pointer to the last element, but it's like one past the last element, somewhere you never want to get to. All right. So if you ask for v dot end, it would take you. It's like a pointer to right here. V dot end. So you never actually want to dereference that. Okay. So that's the thing. But you can work with them like pointers, okay? Iterators are just like pointers, that they have this star operator overloaded. If it is pointing to 8 right now, if it's an iterator to the number, to the index 0, then if you say star it right now, it will give you back the 8, the number 8. And you can change it too. You can be like star it equals 7. You can do that too. So you can do like, you can have it work like that, and then you can advance the iterator just like doing pointer arithmetic on like a C string. You can say it plus plus, and now the t's look like pluses, don't they? So my best handwriting. It plus plus will advance the iterator. Has the plus plus operator overloaded, and now if you say star it, it's pointing to the 6, pointing to the next element. And you want to keep going until you reach end, v dot end, and just like don't dereference it once it hits there though. Okay, so they're kind of like pointers, and let me show you that so far. Okay. Dun, dun, dun. You can implement iterators using pointers. But we just don't care. It's a black box. Vectors.cpp. Dun, dun, dun. Yeah, is there a question before I go to code? Yeah. Yeah, it's one past the end, really. Yeah, that's how you think about it. So let's include the vector library. And I'll make my favorite vector. Make this vector v. Vector int v 8675, and let's get an iterator. Let's do v.begin. So what's the type of an iterator? v.begin, what's that going to return? It's going to return, I want to call it it. The type of it is vector int : iterator. It's a type within a type. If there's a vector of doubles, it would be vector double : iterator. Okay, so there it is. And I can use it like a pointer. Be like, see out star it. It's pointing to the start, so it'll print 8 right now. So there's the 8. You can advance it and be like IT++. And now it's pointing to the 6, the next element. So you see that. Does that make sense? That's what's going on. And you can go through the whole vector this way. You can be like, all right, for vector int iterator it equals v.begin. Keep going while it is not the end. We want to stop because that's one past the end. it++ to advance it. And then just use it. See how, like, star it, like a space. That'll go through the entire thing, right? Until it hits the end and print out all the elements. Does that make sense? It's a little complicated, but that's another way to go through the entire vector. Any questions about that? That's kind of nice. The magic of iterators is going to become very apparent with things other than vectors. This is kind of silly because we know indices, right? There's another way to do it, and it's a more common way. But this is another way to go through the vector. And actually, when we use that range-based for loop, if you say this, for every int x in v, and then do something with x in the body, this syntax, the compiler is secretly translating into a use of iterators. So this code, like if I did it with this kind of code, with a range-based for loop, it would turn it into this code, really. That's pretty nice, all right? We're getting that for free. We don't even have to remember it, okay? So that's what's going on. Now you know the secrets. Let me kind of draw how you could think of vector iterators being pointers. They could have been pointers, all right? And maybe the standard library is implementing them using pointers. We just don't care. It could be anything. There's plenty of ways to implement iterators. Just a way of getting through this vector. But think of them like pointers. Why not? So here's my vector v, 8, 6, 7, 5. And if I ask for like it equals v.begin, maybe that's going to be a pointer to the start of v. Like let's say that's address 100. If these are ints, this is 104, 108, 112. And then it at the start would hold 100, right? And then it++ would just like advance the pointer, make it 104. The next int address, 104. it++ again would advance it. Then star it, of course, would give me the actual 7. It could have been a real pointer. It could have been 108, right? it++ again makes it 112. And then it++ one more time is one past the end, and that could be the address that v.end gives back. Just that silly address that's one past the end of this vector in memory. And then we just know to not go there. It could have been using pointers. So we could have gone through like all of them and like printed out. That's how it could have printed out, like star it when it was 8, when it was 6, when it was 7, when it was 5. Okay? So they may secretly be using pointers, but there's other ways to implement iterators. It's kind of like a pointer. It's a wrapper around the idea of iteration. Okay? So that's an iterator, and it works for vectors. It's going to work for the other containers too. So are we good with this? Are we ready to go on to a new container? Something other than vectors? All right. So let's do list next. There are lists. Here's a list class. It looks exactly the same as vectors, more or less. Okay, let me show that to you. So lists are a wrapper around. Again, you don't really care about how they are actually implemented. You just care about their operations. So a list class, you can do the following. Look at the constructor. You can make like a list of ints, starts out empty, and you can add to it, let's see, with the push back as well as push front. We didn't have push front for vectors, did we? You have them for lists. Here it is, doing push front and like building stuff at the start. That's pretty nice. And look at a use of iterators in the same exact way. That's where the power comes, okay? So we're going to get there. So it looks the same as vectors, like list of ints. Make me a list of ints, please. That's going to be similar. And this is where iterators are useful. All right? You might be wondering, like, why in the world do I ever need iterators? It's very complicated. I can go to indices. For the list type, there are no indices. All right? These iterator things are going to work the exact same way for completely different looking things, like lists. So they still begin and end. There's iterators for lists. And the secret is the lists are a wrapper around a linked list. So like if you build this list, 8675 again, it looks like this in memory. But we don't care. We just know that it responds to our commands. in the way that a list should. I can add to the start as well as the end. I can pop from the start as well as the end. So lists are an AUT that respond to these commands. Push back, pop back. Then you can also push front and pop front, which is really, really cool. They know their size as well. And insertion and deletion to the back or the front, which we know is very hard for vectors, are constant time. So like pop front, that's really hard to do in a vector. Constant time to remove something from the start of a list. So that's the trade-off. If you want to be able to do that quickly, add things to the start as well as the end, you better use a list. Okay? If you want to go to the middle very quickly, then a list is maybe not the best thing, because you know, like linked lists, you got to start at the beginning and work your way. Okay? You can also go backwards. But that's what a list is all about. Let's look at some of their code. It's very, very similar. It's going to look very, very similar to vectors. I will include not the vector header, but the list header. All right, now I can make a list of ints. Call it L. And I can push back, just like I could with the vector, right? 3, 4. So now it's the list 3, 4 in that order. But I can also push the front. I can say push front 2. And now it's 2, 3, 4, right? Push front 1. Now it's 1, 2, 3, 4. Does that make sense? And to display what's going on in that list, I can, of course, iterate through it with an iterator. It's really nice. There's no .at for lists. There's no concept of indices, but the iterators, the nice people of the C++ standard library, have implemented the iterators in the exact same way. All the syntax works. If I have my list that I've made, I can go through it in order with the begin and the end, all right? Using a loop and be like, all right, list event : iterator it equals L dot begin. Just points it there somehow. Star it right now would give me back 8, right? Star it right now would give me back 8. Or I guess I've built up, what I've really just done is built up the list 1, 2, 3, 4. So let's use those numbers. That's what I did in the code. We got the list 1, 2, 3, 4. Star it would give me back 1 right now. And then it++ all over again, plus plus, would advance the iterator to point to the 2 list element. Could be stored as a linked list node. Isn't that gorgeous? That's going to be exactly the same. Everything's going to work in the exact same way. It can be it++ all day long. And then what's 1 past the end? What's like L.end? It's like the end of the list is like null, the null pointer. So maybe secretly it's holding on to null when like you've gone past the end. Who knows? But you can use iterators in the exact same way. All right, so let's do that. It's going to look exactly the same. It's going to be, all right, for list of int : iterator it equals L dot begin. Keep going it until you're the end. Stop when it's the end, L dot end. Don't keep going then, but it++ to advance it. And then what do I want to do? I want to use it to get at each element. See how it's star it space. So a completely different thing in memory, but the iterators work the same. That's very, very nice and very, very powerful. There's my 1, 2, 3, 4. It's going to go through it in order. Isn't that nice? And then we also know that this secret syntax is happening whenever you use a range-based for loop. So like most people choose to not do it this way, but you know the secret now. You could have used the range-based for loop on a list of ints. You could have said, all right, for every integer I in the list L, this will transform this code into a use of iterators. Just use I. This is going to get turned in to the code above it. Isn't that nice? These two lines, these two for loops are exactly the same as far as the compiler is concerned. It's going to turn one into the other. Because these iterators exist. Begin and end exist. It's going to do the exact same thing. It's very, very powerful. It's a completely different container. It's working in different ways, has different operations. Oh man, I can push the front, pop from the front as well. It is glorious, and I can go through it once I learn this style. And now we know it. All right? Any questions about lists and their iterators? That's pretty cool. All right? I got more. Let's do set now. There's a set type. So let's go to that one. Lives in the set header. There it goes. What can you do to a set? You can insert and erase from a set. Again, there's no .at. There's count and find to check if something's in there. So you should read all these things. It's just it's a container that stores unique elements following the specific order. Interesting. So, okay. So a set of t's stores t's in order, whatever the type t is, like a bunch of ints in order. That's fine. So if you make a set, it's really just like a cloud, and it's going to keep track of stuff. What's in there, what's not in there, right? The commands that it will respond to are like insert, count how many things of that number are in there, erase from the set. So like, let's say that I want to insert the following numbers in order, in this following order into this empty set S. I want to do insert 2 again, insert 1, insert 3, insert 0. What will happen is, all right, it inserts the 2. That's the very first thing. It's like, all right, I'll put it right here. Then if you see you want to insert the 2 again, there's not going to be 2 2s. There's only ever 1 2. So this one does nothing. Okay? It's unique elements. It's only keeping track of, was there a 2 in the set or not? There is 1 already. It doesn't have to do anything. If you add the 1, it's going to place it in order as well. It's like, all right, the 1 comes before the 2. If you insert the 3, it's like, okay, the 3 inserts after here. It's the biggest thing. They insert the 0, it's like, all right, it's got to go right here. So it's also going to keep track of order. And it's only like, was it in there or was it not in there? Duplicates do not count inside of a set. Okay? And all of these operations to insert stuff in this kind of sorted order, essentially, are logarithmic time, just like for binary search. And we know how fast that is, right? That's pretty cool. So insert, you set insert something, like insert into the set here, insert the number 20 or whatever. Complexity is logarithmic in the current size of the set, how many things are in it right now, right? And that's very nice if we get order out of that too. That's pretty cool. Okay, so they're going to know the order of their elements. The insertion takes a little bit extra time. It's not constant, it's logarithmic, so that it figures out where to put the thing. Keeps it in order for you. It's very, very nice, right? You'll learn more about this in CSCI 41. And because of that order, because there's no like .at, if you want to go through the set, you got to use iterators again, and you're going to get stuff out in sorted order. All right. So if I want to insert a new element, if I want to insert the element 42 right now, it would take on the order of log base 2 of 4 basic operations to do it, because it's going to be a logarithmic time in the current size of the set. Okay. So let me show you sets now. Let's look at all their operations. So it's just like, it's a little cloud that you can keep track of, like, was something in this set or was something not in this set. All right. Set, let's make a set of ints. Why not? Call it S, and we'll start inserting into it. Insert, we'll insert 2. What was the order? 2, 2, 1, 3, 0. 2, 2, 1, 3, 0. So there's my set. And you can ask your set, hey, was there a 2 in my set right now? Is there a 42 in my set right now? By asking the count. That's the easiest way. What count does, it's a little weird. This also exists across a bunch of different containers. This is why it's going to be weird for sets. But what it does, it gives you back the number of things set to 2 inside of my set, right? So for a set, either the 2 is in there or it's not in there. There's no duplicate. So what's the count of all the 2's in my set? It's only ever going to be 1 or 0. Okay, so it's going to give back 1. And you can use that like true. Okay, you can use this in an if statement. Like, all right, there is going to be 1 2 in my set. It keeps track of whether or not it's there. No duplicates to count, though. So there's going to be 1. It's going to give back, yes, there was 1 2 in the set. Right? Even though I tried to insert it twice. There is 1 1 in the set. So the count of the 1's is going to be 1 as well. It's like true, kind of, because it's in there. If you ask for the count of something that's not in the set, like 42, 42 is not in the set, so what's the count of all the 42's in the set? 0. So you can use that like false, which is very nice. You can use this in like an if statement. Okay, so that's how you can check if something's there. Because usually you're using a set to like check and see like, was this number in my set? Do I care about it? Is this person, like, you can use this to keep track of attendance or something. Is the person here today? So let's iterate through it with an iterator for every value in the set. So go through it for every set. Int iterator it equals s.begin, right? S.begin, there it is. It keeps going until it's the end. Don't let it get to the end, s.end. Advance it with the plus plus. Still, the same syntax works. See how it's star IT in a space. Very, very cool. Oops. There we go. And sets keep track of order, so when you iterate through the set with iterators, it's giving you back those elements in sorted order. 1, 2, 3. 0, 1, 2, 3. That's very cool. So there's no duplicates in sets. You can just kind of like check if something's there or not there, and you can go through it and get it back in order. Any questions about that? And of course, the range-based for loop works exactly the same. Gets turned into this code, but like now you know the secret. You know that it's going to be turned into this. That's kind of nice. If you need order as well as just like don't care about duplicates, look to a set. That's useful for certain things. All right, we good to keep going? There's even more. Just want to show you a bunch of different containers right now. All right, the last one I want to show you is called map. All right, so a map is very similar to a set. It's like a cloud of things. I can make a map called M. But there's two pieces, there's two types involved in a map. There's a key type and a value type. It's holding pairs of things. You're inserting two things at once. So there's two types in a map. There's a key type and a value type. And we say that the map container maps the keys to the values. All right? So that's very important. You'll see those words come up all day long for the rest of your computer science career. Keys and values all over the place. And here's how you would declare a map. All right? Kind of looks like that. Let me show it to you. Right here. Yep. Let's give a good example with like dot in place or something. You can make a map from characters to ints, mapping characters to integers. So it's like, all right, x maps to 100, y maps to 200, z maps to 100. And of course, you can iterate through that, but it's going to keep track of those things. So a good use case for a map data type is like somebody's, like a phone book. Do we know what phone books are? Because I don't think they exist anymore, right? It's a big book with a bunch of, like, in alphabetical order, people's names mapping to their phone numbers, okay? So a phone book, you could declare it in C++ like this. It's a map from strings, people's names or their keys. That's what you're going to look up. You're going to look up their name, right? Flip through the book in sorted order, and then you're going to map those to ints, right? Those are people's phone numbers. So that's your phone book, and it's mapping names to numbers, right? So that's the key type is the first thing, the value type is the second thing, and when you add stuff into your map, it's going to go in that order. So it's like, it's really, you're putting in pairs. Like I'm going to map my number, like, or my name. I'll put my number in the phone book. Like, so I'm going to add a pair, right? My name string to like my phone number, whatever, 555 something, right? 1, 2, 3, 4. So that's kind of how you're going to put stuff in a map. And you can also insert other things. Like let's say I give my cat a phone. Alonzo gets his own number, 555, 1, 2, 3, 5. So you're just going to put a bunch of pairs like this in your map. And then the first part is the key. That's what you're going to use to look it up later. And then the value is what you get back when you're searching for that key. All right, so that's kind of how it's going to work. And then there's also a sense of ordering to these maps. So just like sets, they're ordered based on their keys. So it really is like a phone book in that sense. You can flip through, like it's going to find it very quickly because you can use binary search in a phone book. It's going to use binary search in the map. Okay, so given a key, you can look up the value associated with it, and that's very nice. Okay, let me show that to you. And how it's used. So it's for lookups. So I'll include maps. And I also want to use the string type. I'll make a phone book. It's a map from strings to ints called phone book. And then I'll put people's names and numbers in it. Question first? So is a map like a dictionary in other languages? Yes. Exactly right. So, all right, I've got my phone book. It's going to map from strings to ints. And here's how you put somebody's name and their number in the phone book. You say phone book dot, it's dot in place. It's a weird word. It's like put it in there, I guess. In place, Lawton mapping to my number. That one. All right. In place, Lonzo mapping to his number. Okay. And then very similar things exist, but it's based on the key now. All right. So you can go and ask your phone book, hey, are there any numbers associated with the key Lawton in the phone book? So you can use .count again, but it's based on the keys type, because you're going to use that to look up the value. Okay, count. Hey, is there a Lawton in the phone book? Is my mom in the phone book? Not right now, right? So .count exists, and you use it for the keys. So again, it's only ever going to be 1 or 0. Is it there or is it not there? You can't map one thing to multiple things. So it's either there or not there. So it's again true or false, 1 or 0. So yes, there is a lot in mapping to something in the phone book. No, there is not a lot in small. Or no. Okay. So you might wonder, how do you get the value? Like the whole point is looking up. What's that? Well, it's the .at. .at, just like for vectors, exists, but it works a little bit differently. It's not an index, it's a key. Look up phone book, the value associated with the key lot. And that's where the maps shine. It's going to give you back the value associated with that key. Does that make sense? That's how maps work. That's what they do. All right. You will get an error if you try to go somewhere that does not exist, like this one. Just like going to an index that doesn't exist in a vector. It's like, oh no, sorry, that one doesn't work. All right. So you can't do that one. Was that a question? No, you can only have one key. So if you do something else, I don't know. It's the second one. Like this one takes priority now. Like it's overwriting it. The key can only map to one value. Yeah. So otherwise, what do you give back when you say .at the key? It's like you give the first one or the second one. It's only going to work for. It's only going to keep track of one. Yeah, so it'll overwrite if you do more. Good question. Let's see. So yeah, you can look up at the value, and these are just as fast as sets because they are going to keep track of the order based on the key. So it's like to like insert something, or sorry, to in place something. There's also insert, but it's a little bit more complicated. It's again logarithmic. To go and look something up with the .at, it's going to like flip through the phone book using binary search. So logarithmic, right? Because it's in sorted order. And you better believe there's iterators for maps. So you can go through your entire type and print out all the pairs of people, name and number all over the place. So let me show you those iterators. This one's going to be a little bit more complicated. So again, there's begin and end. You can go through the thing. You do it in the same way, but the iterator, the IT thing, is not going to give you one piece back, right? It's got to give you two things back. It's got to give you the key and the value. So it's giving you back what's called a pair of things in C++. And IT is like a pointer, so you got to dereference it, and you can go to the first part of the pair and the second part of the pair. That's how they're going to be named. IT arrow first, IT arrow second. Okay, so that's going to be important. But it will go through it in sorted order based on the keys. Okay. So let's do that one. All right, let's make an iterator. For map string, it depends on the type. Map string int iterator. Because this is a map from strings to ints, right? Gotta keep that in mind. For map string int iterator, IT equals phone book dot begin. IT keep going until your phone book dot end and stop before you get there. And then I gotta zoom out. And then IT plus plus to keep on advancing. All right, what do we do with our IT now? It's going to point to each pair, each key value pair now. And we can go and get out each piece. So see out, it's going to be not IT dot first because it's IT is like a pointer. So you got to like dereference it first. IT dot first. All right, that's going to be the key value, and that's going to map to the value. All right, and so that you know that this syntax is the long form of the arrow operator. So if you can use the arrow, it does both at once, dereference and dot. The arrow second, so that's going to be the value. All right, and so that's going to go through the entire thing and print out each key and value. You got two things in it right now, so it's going to go in sorted order based on the key and give you back the first thing was the key, and then the second thing was the value associated with that key. All right, that's what you're getting back if you want to iterate through it in that order. Okay. So that is really nice. Iterators are glorious because we get to use these, right? For these vastly different kinds of containers. They all are going to work. It's really, really nice. It's just a way of going through them. Okay? Any questions about any of that? Yes? Oh, there's a different piece. for each person. So they're like, if maybe 2 people share a phone number, that's fine. They just map to the same number. Yeah. Keys, you only have one key with a certain name though. You can have 2 lines, but you can always map to the same value because everybody gets their own copy of that value. Yeah. Good question. Any others? We've learned a lot of containers, which means I now have a question for you. All right, I have 4 questions in total, so I would like you to get into groups, please, and talk about each of them, so we can just like rapid fire the answers inside of the buy clicker page. Please go there, and I'll stop attendance after we do this too, so make sure to do attendance. Please go to that buy clicker page. It's been a while, and I guess I'll start the little timer for this. But here's my question, all right? Do enter in your answer for one, but discuss the answers to all of them, please, so that we can do the rest just in rapid succession. But as a group, try to discuss what are the best out of these 4 options. What's the best containers to hold each of these ideas? Like, all right, Pokemon cards and their selling prices because they're getting expensive these days as all the millennials become rich. And then, all right, if I wanted to represent a group of people waiting in line, what would be the best container for that? If I wanted to represent a bunch of students on a class roster, maybe for attendance purposes. It all depends on the use case. Which of these should I use? If I want to represent the last 100 days of Bitcoin prices, because we know that fluctuates, which of these should I use? There is not one right answer. So I'm interested in seeing what you think. Is there a question? For all 4 of them? But yeah, discuss all 4, get your answers ready, but just enter in your answer, please, for question 1. Okay? So I'll give you a few minutes to discuss all of them. Give you 4 minutes, a minute for each question. This is a philosophical question. There is no one right answer. Please enter in your answer just for number 1 so that we have it ready to go, but we'll do the rest right after. Are we ready? Like, is that enough time? You guys are ready early? All right, I trust you. Well, let's see what we're thinking for number 1 then. Pokemon cards and their selling prices. How much the original Charizard card is selling for these days, etc., etc. Ooh, look at us. We are very confident that the right answer should be D. Somebody who chose D. Why did you pick that? for Pokemon cards and their selling prices. Sure.
So if you want to like look at our price of a Pokemon card, like the different prices for a Pokemon card you want, just like search up the Pokemon card and then give you a value for that.
So you want to map their name to their price?
Yeah.
Like a string to a double? Makes sense? Yeah, good. But there's plenty of other options, like some of us thought B was a good idea. It depends on what you want to do, right? There is no one right answer. It really depends on what you want to do with these values. So you can just make a vector or a list of pairs if that's all you care about. You just want to keep like a big long database for yourself to look at later, like iterate through later. That's fine. Maybe you wanted to sort by the most expensive prices. Like maybe then it would be a good idea to make a vector of pairs. And then you could sort by the price in the second part of the pair. That would work. But yeah, I think map is a good idea. So you can just like, usually somebody's going to want like, I want the Pikachu card, tell me its price right now, enter. And that would just be a lookup in the map. Does that make sense? Yeah, so it really does depend, but there are good reasons for everything. All right, let's do number 2. Got your answers ready, I assume. So what do you think? Group of people waiting in line. Well, what should we use to represent them if we're going to represent them virtually? I'll give you like 5 seconds because in theory, you have the answer ready. You should be on the same page. 3, 2, 1. All right, let's see what we're thinking. Ooh, see, we're all over the place for this one. Doesn't really, who knows? Now this is important. We are kind of like at a tie between A and B. I think A and B would probably be the best answers. Because if you got a bunch of people in line, like you want to like, maybe this is for like they're waiting to go on a ride or something, right? And so people are going to come and get in line, so you're going to want to push back for sure. So vector and list, they both have pushback, right? That's the thing. Can people cut in line? It depends on the use case. Like, do fast passes still exist at Disneyland? They rebranded, right? And now it costs money or something. But you used to be able to cut the line, right? Maybe you want to be able to push front. Vectors can't do that, can they? So maybe you want to look for a list. I don't know. And then once people are like, they get on the ride, they're finished. I think you always want to be able to pop front. So I think I would personally pick list, because like lists you can pop the front very, very quickly and easily. But there's ways to think of other ones. Like you could use a map for people's names to what like the expected wait time or something. Like it depends on what you're using this for. Does that make sense? There is no right answer, but there are ways to explain and justify. So yeah, good thoughts. Let's do number 3. Students on a class roster. What should this be? How would we represent them? Again, it depends on the use case. Are we going to use it for attendance? Grades? I don't know. Why do we need those names? We have to think about it. So come up with an example scenario and then choose your answer based on that. I'll give you 5 more seconds. 4, 3, 2, 1, 0. Look at us. We're all over the place. Nice. We're thinking B or C maybe. And yeah, let's hear from both people. So somebody who picked B, like why would a list be a good idea? Can you tell me? Why might a list be a good idea to store a bunch of students on a roster? Yeah, that's true. Like if they drop the class, like then you can get them off the roster pretty easily. That makes a lot of sense. Good. Yeah, so there's definitely a valid use case for lists. And then set tied with list. Can somebody who chose set explain why they picked that one over anything else? What was your thought process? Is somebody saying something? I can't hear. There are 5 of you. Do I have to interview each one of you? Find out who picked one? Bless you. So a set just keeps track of things without duplicates. There's an order to it. Okay, we're just too shy today. All right. So I think the fact that there's an order might be useful. Like you're getting things up, you're iterating through your roster, maybe in order based on last names. You're trying to call out attendance. That would make sense to me. You can't have duplicate people, so that's fine. Hopefully everybody's name is different. I think that's okay. Okay, so that makes sense. All right, let's do number 4, last one. All right, last 100 days of Bitcoin prices. Give you 5 more seconds to enter in your answer. What would you use to represent them? 4, 3, 2, 1, 0. Ooh, we are torn. Look at us. A versus D. All right. So, vector versus map. Why might a vector be a good idea? I want audience participation. I'm just going to stand here until somebody says something. Why vector? Why might that be a good idea? Yeah.
Because the values of the Bitcoin prices are going to change once it's in the past.
Yeah, you might want to be like, all right, 99 days ago. That's index 99. Let's go there. That would be perfect. Good. So like, there's an order to it, and you want to keep track of that order. It's never going to like. Time is not going to shift like that. Like, I just want to know a couple days ago, the day after that. Like, it's all in that order. That's perfect. So that's a good thing. And then you can sort it as well. And then, all right, what about D? Why might D be a good way? Like mapping from a certain key to a certain value. Why might I choose a map? Again, I will stand here until somebody thinks of something. Good, yeah, you can have like a date type. Date mapping to, like, I want to know exactly on 11/21/2024 what was the price of Bitcoin. So you can jump around very easily and not have to calculate, all right, if I care about this date, what index do I need to go to? How many days ago was that? So there's 2 good reasons. Yeah, you could use vectors versus maps, and like maybe you want to use both, honestly. Have a copy in each. That's the thing. Totally possible. So very good thoughts, and you can totally use the other ones. There's a use case for these as well if you think hard about it. All right, does that make sense? There's no one right answer, and so I think we noticed that. All right, any questions about containers? Or I switch gears. All right, I got one last set of slides I want to start today. It's a very exciting set of slides. I'm happy to teach it. I promise to stop that. It is about the world outside of C++. I promise to not test you on this, but depending on where you transfer to, like there's a bunch of different schools. UCs, for example, they like to start their students with Python, so you need to know a little Python. Fresno State, they use C++, and so that's kind of why we use C++ first. But other schools, they use Java, and so like you need to know these things. You need to have seen them so that you can like go to that school that you're transferring to and like understand things. I will show you a few bits of both Java and Python. Those are like the 2 main contenders with C++. I will not test you on this. It's just something that you need to know, okay? And it's going to be very nice once I show you, like, what does Java look like? You're going to see that it's comfortably familiar, right? It's going to look exactly like C++. Python's going to look very similar to C++ as well. Like, once you learn one language, you're going to know the rest. It's very easy to learn the rest, okay? So I'm very excited to show you that fact, all right? There are, I'm going to start with Java, very similar to C++. It's an object-oriented language, just like C++. So once you learn one, you know them all, essentially. Okay, so there are some very nice tutorials on Java on the internet that I encourage you to read. Like there's a cool website called learnxandyminutes.com. They've got some documentation, like a quick tutorial for Java, a quick tutorial for Python, like, and a bunch of different other languages. So I encourage you to look at that if you'd like, but it's just a big long file. It's walking through like, here's a bunch of Java, and you learn it as you go. So it's a nice, good introduction if you're coming from another language. So look there if you'd like. But yeah, there's a bunch of fun, plenty of memes about Java because everybody uses it. It's still pretty popular in industry. I guess the meme with Java is like that it's very wordy. Java, the joke about Java, it's a very wordy language. Your lines are very long. You have to say very, very long things to get what you want. But it's still pretty cool. All right, so let me show you Hello World in Java. All right, so as you would expect, it's not hello world.cpp anymore. The extension for Java programs is .java. They just spell it all out. All right, and they really like capitalization in Java as well. So I need to make a hello world.java file. All right, hello world.java, and I will comment it out. We'll go very slowly. So I'll say hello world.java. All right, and I'm going to start typing, and I will explain myself later. Right, I got to say public class, same name as the file, hello world. That's very important. All right, give some curly braces. There's no semicolon at the end. For Java, everything has to be a class somehow, even if I want just a main function. So I got to put the main function inside the class in a weird way, as a static method. That's, for all intents and purposes, a function at that point. Have we read about static, that word? That does exist in C++. Is it in the book? It should be in the book somewhere. It's in the object-oriented programming section. But what we need to make a main function is we're going to say public static void main. It's not int main, it's void main in Java. It doesn't actually return something. And it's going to take the command line arguments. You must explicitly talk about the command line arguments. Capital string, and it's args, and it's not an array of args like that. It's an array of strings like that. It's an array of strings like this, where the array is next to the type name, which honestly is the better way. I think that this makes more sense to me. Like args is an array of strings. Like that should be next to the type. It's part of the type. It should all be together. I like that. I like how Java does that. Right? And then the print, there's no cout. You got to say system.out.println, and then you give hello world. Is there a question? Hello world, semicolon. Yeah, very, very wordy. So let me compile and run this, and I'll explain it, and I'll comment it all up. So it looks it's surprisingly similar, right? You can kind of understand this is going to print something, print a line, print this with a new line, essentially. That's what it's doing. To compile this, you're going to say Java C. Java C is the Java compiler, right? What that's going to do, so I've got my new file. There it is, hello world.java. If I say Java C, hello world.java, and I didn't have any errors, it will create hello world.class. It's a file that represents this entire class. And the main function is baked in there somewhere. To run it, it's a little bit different, right? I guess let me do this in order. So Java is very, very picky. If you say public class hello world, your file must be called hello world with the same capitalization .java. You cannot change that. You will get a compiler error if you use lowercase or do anything different. It's a little weird. It's like, nope, sorry. Hello world is public, should be declared in a file name lowercase hello world.java. So it's very picky, first of all. It's got to be called that. Then it'll work. And that will create hello world.class. And Java is a language that does not produce machine code. It's still ones and zeros. It's still binary, this .class file. It's still a binary file, but I can't say /hello world.class. That's not a thing. It's not machine code yet. Java is what's called a just-in-time compiled language. It's a language with a virtual machine inside of it. If you've heard any of those words, sorry if that didn't make any sense, but that's the moral of that story, is that you must run the file with something else. You have to give it to Java, and then it will translate it to machine code as it's going, like real machine code for my particular architecture. So I'm going to run this file by saying Java hello world. I don't have to say the .class. It'll find the .class. You say Java hello world. You got to run it through Java. Okay. Java hello world. Hit enter. Cool. It prints it out. Yay. All right. That's the secret. Okay. So now let me comment this out. The comments are exactly the same as in C++. So in Java, first of all, everything is a class. Everything is one word. It is a class. If you just want a function like main is a function. If you just want a function, you need to put it inside of a class still. And so there it is. It's got to be a static method, which means it's just part of the class itself, not as part of any object. So hello world is a public class. There it is. Hello world is public. So it's visible to the outside world. To the outside world. All right. That means other people couldn't include it. The word in Java is called import. That means other people could import it if we wrote other things, import it and use it. All right. So that's the moral of that story. So that's what happens. So hello world is a class. It exists. It doesn't have any normal method. It has a static method, and that's your main function. Right. So the main function in quotes now, the main function lives inside the public class associated with this file. I've got to be very wordy today. You have to use this exact definition. You can't be like, all right, I don't care about the command line arguments. I'm not using them, so delete. No, got to be like this. You must use the definition below. Always. Args are your command line arguments, and even if you don't want them, you got to declare them. Right? Args are the command line arguments. So you can get them there. It's a bunch of strings with a capital S in Java. Even if you're not using the command line args. You've got to do it. Right? So there's that. In Java, args is an array of strings. All right? Java strings. There's that. Main is a public method inside the hello world class. Oops, with a capital W. Class. It's also called static, and that makes it function like a function. All right? It's also static. And what that means is it's part of the class itself. It's not part of, each object does not get a main function. It's like this is baked into the class. There's just one copy of it. And that's essentially what it means to be a function, right? So it's also static, which means that it belongs to the class itself rather than to any object of the class. Nobody's making any objects of the hello world class anyway. So there's that. And then finally, there's no such thing as declarations in Java for methods. You don't have to declare anything. Any functions / methods in Java, even if the thing you want to call is implemented below you, it'll just find it, which is really nice. I wish C++ worked like that. It just finds them no matter what order you put them in. Okay? So that's a lot of comments. They also have the multi-line comments. This also exists. That's a thing. Bless you. But that's hello world in a nutshell. It's got to look exactly like that. And this is a function in a library that's just by default you get imported. There's no IO streams. It's part of the system library. That's you get that by default. And if we go to their documentation page, we can go and look at it. The Java standard library, you guys, is next level. It is the greatest thing ever. Look at all these classes. So many more than C++. It's amazing. And this is just part of java.lang. That's the default thing. There's other things. We'll get to those. Java.lang has system inside of it. There's a system class. Inside of system, there was out. Out was like an O stream, essentially. It's called a print stream in Java. Out was a print stream, and what can you do to a print stream? What methods does it have? Well, one of which is a println. Println down here, println on a string. It's all right, it prints the string, and the ln part means it adds a new line at the end. See how I didn't add the new line? It does it for me. There is just a normal print if you don't want anything after it. Just prints the thing, whatever it was. No new line. Println, though, gives you a new line. And look at all this lovely documentation. I can print it, click on it, and it's telling me stuff. This is automatically generated from the source code for the Java language, actually. This is very, very nice. Very, very useful stuff. So Java's got a lot of cool stuff baked into it, and that's why people like it. All right? It's fun to teach with. So, yeah, that is hello world.java. Question? Do I prefer? I hate Java, honestly. I like... it depends on the use case. I'm really good at C++ because I have to teach it every year. So I like that one. I am partial to functional programming languages. So one day you'll learn about those. You got Haskell, OCaml. There's one called Scala, which works on the Java virtual machine. I used that during my grad school years because my advisor really liked that. But I love functional languages and functional programming. One day you might too. JavaScript is the simplest language that is very functional. So if you like JavaScript, you might enjoy the other functional languages that exist in the world. So yeah, I like those. But yeah, I just usually if I'm writing something for myself that's quick, I'll just use Python. What's that? It's just very wordy. I don't like the wordiness. I don't like this. Everything's in its place. I respect it. There's times where it's useful, but I'd like to get the job done quicker, I would say. But yeah. If I look to something on the Java virtual machine, I'd probably just go with Scala or Kotlin instead. But Java like paved the road for a lot of things, paved the way for a lot of things, and so it's useful to learn at the same time. Like it's good to be like to spell things out when you're learning. I definitely think that. Yeah, but it's all just it's a matter of what you think as a person, I guess. Question? It tells it to be a function because normally this would be a method, right? And somebody would call it like this is it's still a method. It's a static method though. It's part of the class itself, and so there's only one copy of it. It's not like each object gets a copy. It's just you get that one. The class has it. It's part of the class. There's just one thing.
So if you didn't put it, you think it would, the program would think it was an object? Or like,
Yeah, if you did it like this, like let's say that we did have a function here. Sorry, we had a method here. So first of all, to call a method, you have to make a hello world object. So hello world h. I don't know. If you made a method, it would be like public int blah return 42. Then you could say h.blah. There's no such concept of h.main right now. The main does not belong to hello world objects. It's a static method. It belongs to the class. It's really hello world dot main. It's part of the class name. That's kind of what that means. I'll have to defer to your book to explain the rest. But that's the same thing exists in C++. That's a great question, though. Yeah, any other questions before I show you one more example? There's more next time, too, though. So let's see. Yeah, so here's just a bunch of words. So pretty much everything is a class in Java. You think of it that way, at least. There are no such things as pointers. They're called references, and I'm so sorry. They work like pointers, kind of. Arrays look a little bit different. Let me show you an example of stuff, like the types that exist. Okay? They're going to look very, very similar, right? It's going to be deja vu. So here, let's make a new Java file called morejava.java. I can't do that. Sorry. Let's see. It's got to be public class more Java, right? And then if I want a main function, it's going to be public static void main string bracket bracket args. Cool. And so all these types exist, like int. Int is a type. Int x equals 42. Double is a type. Double y equals 3.14. That's still normal. It's all the same. Bool, instead of bool is boolean. They spell it out. Boolean b equals true. Still lowercase true and all that. Strings is a capital S for strings. Baked into the library. It's not, or it's baked into the language. It's not part of the library. So those are those types. What else? Arrays, they look a little different. Let's see. Arrays have to be made on the heap. I guess let me do this in order, sorry. So first of all, before we get there, it's kind of what I was saying over here with you got to run it inside of Java. Java runs on what's called a virtual machine. It's called the Java Virtual Machine, or JVM for short. And so when you compile with Java C, it's not really fully compiled to run on your architecture, on your CPU. It's not ready for that yet. It needs to be compiled one more time, kind of, into something that your operating system can run. All right. So that's different from C++. The compiler G++ makes it straight into, you can run this right now on your machine. For Java, that's not true. You need the Java virtual machine to make that happen. So here's kind of what's going to happen with this file when we compile and run it. Morejava.java. That's my file with my English looking code, right? Public class, whatever. When I compile that with Java C, it's going to make more java.class. .class, and it's still binary. It's closer to the ones, it is ones and zeros, it's still binary. It's closer to the machine architecture, but not quite, right? It's called Java bytecode. It's very quick to compile deep down into machine code, but in order to run this file, we got to give it to the Java command, which runs it in this black box called the Java virtual machine, right? Java virtual machine. So you have to install something. You have to install Java if you want to run a Java program. That's not true of G++. You can give your compiled code to anybody. They can // it. You must have Java installed if you want to run a Java program, because everything must go through here. Okay, that runs the code for you. And so there's trade-offs. It takes a little while longer to run an equivalent Java program because of this, because it's got to be like translated on the fly inside of here. So that takes a little while longer, but it's still on par with C++. Slightly slower. But an upside of this, of doing it this way, is you can give this one file to an ARM device. You can give it to an Intel device. You can give it to Windows. You can give it to Linux. Every Java implementation uses the same compiled form. That's the key. You compile it once and you can run it anywhere. That's not the same with G++. If I compile something with G++ right here, it's going to work with Intel 64-bit Linux. It's not going to work anywhere else. With Java, it will work anywhere Java is installed. Okay, so there's that. Let's see. Every array that I make has to be on the heap. The heap is being used all day long in Java, which is unfortunate, or fortunate, depending on how you think about it. So arrays must be made on the heap. And the type is a little bit different. It's part of the type. Like, it's all connected. I like that. So that the bracket goes after the type. So there's that. And also, all arrays in Java, even though it's just an array, they know their size, which is very useful. So here, let me make an array of ints. So it's going to be int r, not bracket here, but it's an int array called r. I love that. I wish C++ did it that way. It's got to be made on the heap, though. You got to say, all right, I want a new int array, and then you can get the values between curly braces, like, all right, 1, 2, 3. So you can do it that way. And the size of the array is if I'm calling this r, it's an r.length. It's not a method. It's like it's like a member variable, essentially. There's that. What else? And so, got to make that on the heap. Got to say new, and I can iterate through this in a normal way. Like for loops, of course, exist. So here, be like for int I equals 0, I is less than r.length, I plus plus. System.out.println r of I. Right? That syntax is all there. And if I want to compile this, Java C more java.java, that creates more java.class. I can run that with Java more Java. 1, 2, 3. Beautiful. Does that make sense? You might think, like, did I just leak memory, though? Like I said new int, I never said delete. The beauty of Java is that you don't need to do that. Java is what's called garbage collected. And so if you say new all day long, that's fine. You're kind of forced to in Java. All these things being made on the heap, you're making them all day long. Java forces you to use new a whole lot more than in C++. But it will call delete for you. The garbage truck will come, and it will notice when you're done with something, it will never be used again. It'll just figure that out. It's very, very powerful, very, very cool. And this is why we don't teach you Java first, because you would learn bad things, right? You'd have bad manners with your memory management, because you wouldn't know when to delete something. So that's why we go to Java second. Now you know it, all right? But it's garbage collected. It'll figure out when something needs to be deleted, and it will delete it for you. That's also one of the reasons why Java is a little bit slower than C++, because you would do it yourself in C++. It takes some time to notice stuff in Java for the garbage collector to run. And so, yeah, one last thing is no delete is necessary. Very nice. So in Java takes care of deletion for you. It'll call delete. There is actually no delete in the language. You can't even do it if you wanted to. It notices when we're finished, like when we'll never use this again, when we're finished with heap memory and garbage collects it, gets rid of it, which is beautiful, right? So it's impossible to have a memory leak in Java, essentially, which is nice. That's why a lot of people like it and use it in industry. So yeah, I think that's what I wanted to say about Java for now. There will be more of that next time. Then also teach you some Python too. You've never learned that. Are there any questions about this before I switch gears one last time? Because I got to release stuff and talk about finals and stuff. All right. So consider that little tutorial there. All right, let's do your lab first. Lab 10. Second to last lab, I think. This is the square root one. I promised it. All right, let's do it. Start code 40. What's that difficult? Lab 10. Oh, because I'm in Vim. Excuse me. Here are the files. Cool. And you're going to do exactly what we were talking about in class, right? I told you, we talked through it, right? We talked through the process of calculating square roots from scratch. This is what we're doing, all right? We're going to compute square roots by guessing, all right? By that binary search style guessing process, all right? So you're going to be implementing the square root library. So square root.h, here are your two functions. Square root is the one people are going to call, right? Give you some number, whatever it is, you return back the square root of that number. And we're also going to need this approx equal function because you're going to check for, like, is the answer close enough? And you're working with doubles, so we might as well make a function like checks, are A and B close to each other? Are they equal enough? Because they'll never be exactly equal. You can't use double equals, but we need some concept of equality. So we're going to use that too. All right? So approx equal, you're just going to implement those in the CPP file. Approx equal, I want you to return true if A and B are within this much of each other. Very small amount, so they're like practically the same. It's close enough for our purposes because we want a square root within 6 decimal places of precision, let's say. That's what we want. So you'll use approx equal in your square root function, right? So fix that. Got to use like absolute value, right? Subtraction, check those things. That's that. Return true, and two doubles are very close to each other. And then for square root, you're going to do this from scratch. You cannot call sqrt from the math library. I've made sure of it. And you're going to have to start from like a low guess and a high guess. All right. So for square root, it's going to make guesses until your guess is approximately equal to the right thing. Okay. So because this function is increasing, you're never going to like miss the answer. You're eventually going to zoom in until you find it. Okay. So that's the point of that. And yeah, the last thing before I show you like the process and talk about it again is square root. There's no such thing as a square root of negative numbers. So I want you to throw a runtime error. You can put whatever string you want inside of that runtime error, but I want you to throw a runtime error, please, if the user asks you for a negative square root, because that's impossible. Okay, but if you get 0 or above, now you do it. Okay, so what you do at the very start of your function, what you got to do is set up your search space. Like, where should this answer be? I don't know the answer yet. Like somebody called square root of 5. I'm not sure where the answer is, but I know that it's between 0 and 5. Does that make sense? That's where you must start. So your search space should have a lower limit of 0 always. That's always correct. And an upper limit of max of 1 in x or x plus 1. Because remember that the square root of 0.5 is bigger than 0.5. So you can't be like, all right, the square root of 0.5 is between 0 and 0.5 because you'll never find it there. Does that make sense? So you have to use like a max or something for those small values. Because the square root of like a smaller value is bigger than that value. Surprisingly. Okay? So either one of those, use that. So you've got your limits, like somebody asked you the square root of 5. Low and high is that. And then you're going to start guessing in the middle, right? 2.5. You're going to try and check that, hey, is 2.5 squared? Is that 5? Is it approximately equal to 5? If so, I'm done. Otherwise, all right, was it too high or too low? And then you'll move around based on your midpoint. Okay, so that's what's going to happen. Just like repeatedly calculate the midpoint of your search space and check and see if it's close enough. using a prox equal, because you're going to square it, right? You don't have square root. You're trying to compute square root, but you can square your value. See if your current guess is close enough to the answer with a prox equal. Right? So that's what you're going to do. And I have tried my best to give you a very good example. Right? So this is how your program should work when square root of 9 is called. We know the answer for square root of 9 is 3. Let's watch it work. All right? You don't have to print anything in your code. I'm just like, here's what should happen on each iteration, because you're going to have a loop until it's the right answer. Okay? So when x is 9, like if somebody calls you, I want the square root of 9, x is going to be set to 9. Okay? So iteration number 1. All right, I'm asked for the square root of 9. What your code should do is set up, all right, lower limit, where this answer is, I don't know where it is, but it's between 0 and 9. That's your low and high. All right? You calculate the midpoint of that, that's 4.5. Okay? And then you check, all right, is 4.5 good enough answer for the square root of 9? So you'll square it, right? That's all you can do. And you'll find that it's way bigger than 9, right? If it was the square root, it would be very close to 9, wouldn't it? But it's way too big, so it's too high. We have to guess lower, which means our upper limit needs to change. 9 is way too big. The answer is not up there. So 4.5 was big enough. That was already too big. So I'm going to change my upper limit to be my old mid. Right? So when I'm at iteration 2, my lower limit is still 0. My upper limit is the old mid. Now it's 4.5. You see I'm zooming in on that answer? I'm eventually going to get to the right thing. Now my new midpoint of that new search space, this is what your while loop is going to be doing, midpoint of that is this average, 2.25. All right, let's check and see if that's a good enough guess for the square root of 9. Well, we'll square it. We'll find that it's 5. It's much smaller than 9, so it's too low. That means my lower limit was a little too small. It's above that, so this might as well have been my lower limit. Okay, so that's what I'm going to do. I'm going to change my lower limit to that old mid. So now it's in the next iteration, lower limit is 2.25, upper limit is 4.5. I'm cutting off half the search space each time. I'm zooming in towards the answer. Right? The midpoint of that is now 3.375. Squared, it's a little too big, a little bit bigger than 9. It's not approximately equal yet. So, all right, that means that this is a better upper limit. 4.5 is way too big. All right, so this will be my new upper limit. Right, so iteration number 4. This is my lower limit and upper limit, 2.25, 3.375. What's the midpoint of that? What's my new guess for the square root is the midpoint always. Now it's like 2.8-ish. Square that. See if that's close. Now it's a little too small, so we'll guess higher. We'll change the lower limit to be that mid. All right, and so you're just going to keep playing this game, and it's going to zoom in closer and closer to the right answer with more and more decimal places of precision, and eventually it will become close enough that a prox equal returns true finally. All right, so scrolling down, eventually, like the lower limit was this, upper limit was that. Square it. It's a little, still a little too low. It's still a couple decimal places far away. We'll guess higher. We'll change the lower limit to be the midpoint. And then, all right, here we are. Lower limit's that, upper limit's that. After all these things, iteration number 25. What's the midpoint? It's this. Square it. It's that. With 6 decimal places of precision. Then a prox equal will return true, close enough. And so you're going to return mid as the answer for the square root, because that is the right guess. Does that make sense? That's what your code should do. You'll come back to this. Just read it off. You can print it out like this if you want to, and that will help you find the answer. Right? So eventually the middle of your search space squared will become approximately equal to the thing you want to take the square root of, and that by definition means you have found the square root. Okay? That's the secret. That's what you got to do for this one. Any questions about that? Make enough sense? I'm just going to stare at this example until you get it. I'd be happy to draw more stuff with you. But yeah, once you got it working, I've made some tests for you. I've got you a make file as well to compile it. So here's the tests. And I've got a few of them ready, good to go, just making sure that it's correct. Square root of 2, square root of 0.5, square root of something negative, just checking that it threw an exception. Once you've got my tests passing, I want you to write 4 more. So come up with some more numbers and add some more tests. I made a class of tests this time. Why not? So there's just a bunch of test methods. So to add 4 more test methods, please. Call assert true with some numbers. Check them in this kind of way. You can even do an exception testing one if you want. But I would like you to make 4 more tests after you get mine passing. And so I want to see passed 7 times, I think. 3 from me, 4 from you. All right? So that's pretty much it. I think... That's all I want to say. So you're going to include your library implementation as well as the 4 tests that you wrote. So those are the 2 files you're turning in. Can't touch any others. Okay? Any questions about that? I think that's all that I wanted to say about your lab. Yes? No, I've already given you the make file. It's already good to go. So you can just say make square root test, and it will do everything correctly. Yeah, so the make file is already ready for you. So there's that. And yeah, so those are the 2 things that you'll turn in. Keep track of the due date, whatever it was. I don't remember. November 30th, apparently. All right. And that's a little bit, that's the Saturday, because remember that Friday is a holiday. So like I'm giving you a little bit of extra time. Just remember this is going to be due on a Saturday. Okay? You have an extra day to do it. Just get it done by then, please. All right. So if we're good with the lab, there's one last thing before my voice runs out. It's a lot of talking for me today. I will shut up in just a second. We got to talk about your final exam. All right? So we're on week 15. There are 17 weeks of classes. So there's next week. We also have the holiday next week, which is nice. And then week 17, there's still going to be lectures. All right? That's the last week of lectures, last week of classes. And then week 18 is finals week. If you've never had a finals week before, it's just a week where there's nothing but tests. There's no lecture, but you're going to come to class to take a test, right? You're only coming for finals. And so let me release 2 things now. For the week 18 module, you should be able to see them both. So final info and then one last extra credit assignment. All right. So here is our final. It's just like a table from the school. It's a little bit less than our normal class time. The final will be from 2 p.m. to 3:50 p.m. in this room on the Tuesday of finals week. We're just going to get over with on the Tuesday. So December 10th, that is when our final is scheduled to be. So we'll all come to this room and take it. Right? That's when it's going to be. And you're going to get, it's a little bit longer than a normal final, than a midterm. We get an hour and 50 minutes to take a final. So it's going to be a little bit of a longer test. But then there's no lab after that or anything like that. That is it. Like some people are going to have another final at 4 maybe that they have to run to. So there's that. Okay, so that's when it will be. Here are the topics. I can't say that it's not cumulative because you know that everything in this class builds on top of itself. So just like expect to see stuff from everything, right? We'll have topics from everything. I will try to ask more about the stuff that I haven't asked you about before, stuff after the second midterm. But you should still expect to see everything. Like, of course, you're going to have to loop, right? Even though that was from midterm 1. So you should be familiar with everything from the first 2 midterms. And then here's all the new stuff, right? Dun, dun, dun. For pointers in the heap, one thing I do want to say is I'm not going to talk about anything I didn't talk about in lecture. I'm not going to ask you about anything that I didn't cover in lecture. For example, I'm not going to ask you any linked list questions on the final. I'm not going to ask you about destructors on the final. But you need to know those things for 41. That's why I'm having you read it, okay? So all those concepts up to bitwise, that's like the last major concept I want to test you on. If I ask you about anything else, like containers, for example, something after that, right? It'll just be an easy question. I promise that this is the last thing I'll hit you hard on, okay? That's what I want to say. And yeah, the format is exactly the same as a midterm. So the rules are always the same. Keep it all in mind, but you can still use the book, use your notes, stuff like that. And then here's a sample final. Okay? So I think that's what I wanted to say about the information. Does it all make sense? That's what it's going to be, what's going to be on it. All right. We're good? All right. So the last thing is there's one last extra credit assignment. So the finals happening on the 10th. This will be due midnight on the 9th. Let me make sure I did that right. Looks right. Yeah. All right. So your last extra credit opportunity, if you would like, is for the big bucks. This is worth up to 5% extra credit. Again, no late submissions. So again, you can make one last review video if you would like to. All right. So go over a bunch of stuff that might appear on the final and post it here, and your peers will love you forever. It's also a good excuse to force you to study, right? So yeah, as usual, just like make a bunch of examples. Talk about like how to solve the problems that you're posing, right, to the class. So just like maybe pretend to give a little mini lecture, whatever you like to do. Go over some examples, solve some problems, and that's a review, right? So if you want a quarter of the extra credit, if you want 1.25%, make a 10-minute video. If you want 2.5, make a 20-minute video. If you want the full 5, make a 40-minute video, right? So those are your requirements. And just make sure that you have to do something extra to do extra credit. I know I say that every time, but it's very important. So you can't like read off your lab answers, read off my slides that I worked hard to make and you didn't, right? You have to do stuff yourself. You got to make up your own new examples, write some new code. It's never been seen before. Draw some new diagrams, some combination of those. Okay. So ask me if you have any questions about whether or not like this is original enough. Like I'll definitely be able to give you some pointers there. Okay. So yeah, that was my final warning. And yeah, just post a video. Everybody will love you, and it's a good way to force yourself to study too. Okay. So I think that's what I want to say. So this will be due the midnight before the final. So midnight on Monday, 11:59 p.m. on the Monday of finals week. All right. And I think that's everything that I wanted to say. So we'll come here. You'll take it just like a midterm. Be on Canvas. Any last questions? All right. That's all I got.